Hello, I'm Andrew Kucher, and today I'm going to be solving problem 1.31 from the 8th edition Fundamentals of Heat and Mass Transfer by Bergman and Levine. I'm just going to read off the question so you guys have time to read it on your own or listen to me. Consider the tube and inlet conditions of problem 1.30. Heat transfer at a rate of 3.89 megawatts is delivered to the tube for an exit pressure of 8 bar. De- Determine the temperature of the water at the outlet as well as the change in combined thermal and flow work, mechanical energy, total energy of the water from the inlet to the outlet of the tube. And a helpful hint here is given that as a first estimate, neglect the change in mechanical energy when solving part A. So, what is known, first of all, I copied the schematic and known information from problem 1.30, in which it is given that the mass flow is 1.5 kilograms per second, the diameter is 110 millimeters, the length of the pipe is 12 meters, and the T in and P in are 10 bar and 110 degrees Celsius. Key assumptions, it is steady state conditions, and as given from the hint, there is negligible change in kinetic and potential energy, and that there is a uniform velocity at the inlet and outlet. Otherwise, it would be difficult to assume we couldn't use simple math to figure out the velocities of the flow. So we're going to assume uniform velocity to figure out the velocities of the flow later on. And some initial properties here. First of all, using the temperature at the inlet, we can figure out that the pressure density of the liquid is 950 kilograms per meter cubed. And from the pressure, we can also figure out the saturation temperature, where the water will start to become a gas. And using that saturation temperature, we're able to figure out that the saturation enthalpy for a liquid is 762.81 kilojoules per kilogram, and that the CP at that same temperature is 4.3 kilojoules per kilogram Kelvin. There's a CP down here. Now, for the analysis, I sort of dissected the standard mass balance, energy balance equation rather. So I have up here, you have the standard U plus rho specific volume plus the kinetic and potential energy terms. Obviously, the U and rho density times specific volume turns into enthalpy. And as said above, neglect kinetic and potential energy. Once you do that, you're left with m dot change in energy in minus m dot change in energy out plus the thermal energy Q equals 0. And again, simplifying that even further, you end up with just the enthalpy in minus the enthalpy out times the mass flow plus the thermal energy equals 0 because it's steady state. So because the enthalpy in is going to be less than the enthalpy of the saturated liquid, because the fluid in is water that is of a lower temperature than the saturation temperature. We need to figure out what the enthalpy of that water is. So using this equation here, we can calculate for that enthalpy going into the pipe, which, as I state here, is 462.2 kilojoules per kilogram. And then once we know the enthalpy going in, we can easily find the enthalpy going out of the system. And then that value is 3,056 kilojoules per kilogram. Now, that's not what part A is asking us for. Part A is asking us for the temperature. However, we now have two values which with we can find the temperature. We know the pressure at the outlet and the enthalpy at the outlet. And using steam tables, we are able to figure out that the temperature at the outlet is 300 degrees Celsius. Now, part B is pretty simple because up until this point, we're assuming that there's no change in kinetic or potential energy. So E in minus E out is basically just going to be the amount of thermal energy put into the system, essentially, which in this case is 3.89 megawatts. The now calculating for mechanical effects, as stated in the problem here, mechanical energy and using the mechanical energy to find a total change, we need to find the speed of the water at the inlet and the speed of the water at the outlet. Speed at the inlet is pretty straightforward because, again, we have the density of the water. So all we need to do is divide the mass flow by the density times the area of the inlet, which pretty simple math. You end up with 0.166 meters per second. Now, the analysis for the outlet is more tricky because we don't have the density of the water going out of the system because it's not water, it's steam. However, we can change up the equation to instead of calculating for the equation with density, we can now use specific volume. And as I show here, that's the equation. Now, to get the specific volume of the outlet temperature is actually somewhat tricky because many of the steam tables will not choose an 8 bar temperature. So here I basically just calculated for the outlet specific volume by calculating doing linear interpolation on the steam tables at a higher and lower pressure, in this case 7 and 10. So I found the enthalpy at 300 degrees for those two uh, pressures, and then did another linear interpolation between those. So I ended up with a V out of 0.3335, and plugging all the values in, we get a final velocity out of 52.6 meters per second. Now, to get the mechanical energy, you basically just bring back the terms that we lopped off beforehand. And in this case, the obviously gravity stays the same, but the change in height position between the inlet and outlet can be assumed to be the length of the tube. I know I labeled it going horizontal, but in this case, we're going to assume that it's vertical. I just labeled it horizontal because of saving space, essentially. And once you plug in the values from above, you end up with a total change in mechanical energy of 2.25 kilowatts. Obviously, that's a lot lower than the thermal energy put into the system. However, to get the total energy change, you just add the change in mechanical energy to the change in thermal energy, and you get basically the same value, but add on a couple more digits at the end.